Hey everyone, this is section 1.3, Propositional Equivalences in Discrete Math. I already have it written out because I accidentally recorded it in portrait mode instead of sideways, and I'm just having to re-record it so it looks good on YouTube. Anyways, we didn't do 1.2 because we didn't cover that in our class at Chapel Hill. We only did 1.3. We did 1.1 and then skipped to 1.3. So this section is super short. Just a few things. Make sure you read your book and all that, but this will definitely make everything a lot just clearer when you're going through reading or listening to your professor. So first of all, a tautology is a compound proposition that is always true. So it's always going to be true. So no matter what proposition you give here, this is just an example. You can find more online, but this is always going to be true. Say your proposition P is P is equal to Zach has a dog. Okay, this is true. Okay, I have a dog. So this is going to be true. So no matter what you put in here, this is going to be a true or false because it's negating it. So if you look at like a truth table of or, right? No matter what, when you have like a T and a true and one, it's always going to be true. In this one right here, there's no T, so it's always false. So basically just like it shows you that like whenever there's a true, since Zach has a dog is true, there's always going to be a true. Now I'll just say this is false right here. False instead of true. Still, it's going to be false and then true because it negates it. So, it's still, there's always going to be at least one true in there. And it's always going to be true. Always going to be true. Now, the second is the opposite of it. It's a compound proposition that is always false. Remember, like a proposition is a statement that is always true or false. Say, Zach has a dog. Say that is false, right? So you plug it in, it's going to be false and true. Well, if you look at false and true, there's always going to be a false. And if you look at an and true table, whenever there's a false, it's going to be false right here. True and true is never going to be this case right here. It's always going to have a false in it because you have this negation here. That's why it's always false. Those are two big terms you just need to know for this chapter, tautology and a contradiction. Also, there's this next little thing called a logical equivalence. It says that the truth table, the truth value is the same in the truth table. So basically what that means is we're going to have in this chapter, don't really pay attention to this yet, I'll go over this in a second, but basically we're trying to prove that these two are equivalent. Remember, we just learned what this means. This means they're equivalent. And you prove these are equivalent by looking at the truth values. And when we proved it, I'll go over this in more detail in just 1 second. These are all the same in these two columns. So basically it says that the truth value in the columns, are the same in the truth table. That's how you can prove that they're logically equivalent. And you can write this in between. You can write this in between two compound propositions if those columns are the same. So now we go, how can we prove? And I'll show you that truth table right there. So basically, this is an example. We have to prove that this compound proposition is equivalent to this. So instead of using a proof for something, you can use a truth table. That's one way. That's the easiest way, but sometimes your teacher will require you to do proofs, but those are just, I'll show you how to do that, a trick for those at the end of this video. So first you write out your PQR, which are being used in here. Little trick, how when you see a normal truth table, you only see usually P and Q, and it's usually only 4 up. But when you have PQR, there's a lot more cases how you can combine the truth and falses. It's kind of, you can see it, a little trick to memorize how you can write this out without having to totally memorize it is there's 4 truths, 4 falses. And then the second column, there's 2 truths, 2 falses, 2 truths, 2 falses. And then true, false, true, false, true, false. And it always starts with true. So you go 4, 2, 1, 4, 2, 1, and they flip-flop. It's kind of easy. So first we want to prove this, how we learned in, when we learned about what, this means. This basically means that the truth table is the same for these columns. So first we need to find the truth table column for this. So first we have to find Q and R. So basically you can cover P and look at Q and R. And you just use the AND operator. Remember, an AND operator, if it's false, then it's going to be false automatically. If there's even one false, it's going to be false. So all these have false and false in them, and these are both true, so that's why it's true. And then you can kind of, cover up P, Q, and R, and you can create the statement P, and then so you basically use this column and this column, these two columns right here, to do this. And you OR these because you're ORing these two different terms. And whenever there's a true in an OR, you can write true. So all these have true in them, true, true, but there's two falses here and here, and here and here, and here and here. That's why these are, well, I mean that, like, what's it called? Sorry, this one and this one. This is true and true, and this is true. These each have a true in them. So the only ones that are false are ones that have no truths in them as OR. And then for this column, this one right here, you need to find these two terms before you can AND them, So you first, look at P and Q and do this and OR them. You look in Q and R, or P and R, and you OR these two columns and write that there. Then you have these two columns to AND together. And you look at whenever there's a false, the value is going to be a false. And whenever there's no false, it's going to be a true. That's the kind of the property of an AND operator. And so we can prove these by finding this truth table, and we can prove that they're equivalent by looking at the end result and looking at these two columns right here. And since they're exactly the same, it proves that they are equivalent. That's just a little trick there. Also, these are some logical equivalences. So these all deal with this little operator here that we've learned about today. These are some laws that you need to know. Identity laws. It's just saying, like, if you stick in a proposition here and the other thing is true, that's going to give you the proposition back. Same thing for that. This one is like, these are tautologies right here. No matter what you stick into a proposition here, it's always going to give you a true statement or a false. These are just, laws you have to memorize. Whatever proposition you stick in here, it's going to give you the proposition back. Let's see, double negation, these just cancel out, gives you what you have back. These you can flip-flop. Commutative means you can flip-flop back and forth with the ands. Absorption just means like these get absorbed into these here. These are kind of hard to apply, but you kind of have to do a lot of practice to be able to apply them when you're doing, proofs and all that. These help with proofs. So the one way you can prove that two things are logically, when we're doing this, one way we can prove this is logically equivalent is use a truth table. But you're also going to have examples that your teacher is going to give you where you actually have to prove, these two are equivalent with proofs. And when you do it with proofs, this helps. These rules help. And I have two more tips afterward, or one more major tip that will help with the proofs. But to go along with the proofs, this is the best. You need to make sure you can apply these to your problems. Negation down here, I ran out of room on the camera, so I had to write these across from each other. But these give you a tautology and a contradiction. This tautology, contradiction, so something like that. If you just plug in propositions, try them yourself, you can find out that they're always going to be false or always going to be true. Associative laws, you can distribute, or not, you can move the parentheses over. You can move them over here, like that shows you here, and they're the same. They'll give you the same truth table. Like this will give you, like if you're not looking at any of this here, like if you had this in a column and this in a column, it would give you the same columns like we were proving before. Same thing for all these. This will give you the same column as this, you know. This and this will give you the same columns on the truth table. And distributive law, you can put this P into here. You know, you can distribute it in there, this P into this one. It's pretty easy. And De Morgan's law, that's the most important one. It's the easiest one too. Just when you have this not operator, you can distribute it to this case here, and it knots the P and the Q, and it always flips these operators. So like this one flips it to an and, this one flips it to an or. Okay, just take a second, I'll pause and just screenshot this and make sure you kind of review these and be able to apply them. Last but not least, so like I said, one way you can use this to prove logical equivalence. Other way is when you're using proofs, you can use these laws help, and this is extremely helpful. So it'll say like some crazy example. It'll be like, here's an example. It'll say like prove P and Q is equivalent to, you know, not P and Q, then and R, like not R. It'll just give you, this is not true. I'm just making up, it's just a straight example. But when you're proving, you have to get this into, you have to show the steps to get it into this right here. You know, you have to show how to get it into these steps. And some teachers will be like, nope, can't use a truth table. You actually have to show the steps. And you're like, dang, how do I get this arrow into these type of operators? You know what I mean? These ands and ors. And so memorize these two. Just memorize them. Take 5 minutes after this video. Just memorize them. And basically, if P then Q turns into this, and if P if and only if Q turns into this. And these right here have the same truth table. This has the same truth column as this and this. You know what I mean? Basically, just memorize these, and it's easy. You can easily turn these two, when it gives you a problem like this, you can easily turn these into these ands and ors, and then you can manipulate it to get down to here. And using that manipulation to get down, turn this or something into this, you would use laws like this. So that's kind of how the proofs work. I hope that helps, and you can easily follow along your professor when he's doing examples in class. If you have any more questions, let me know in the comments. Like, share, and subscribe.